fine structure constant is undoubtedly the most fundamental, pure, dimensionless number in all of physics. It relates the basic constants of electromagnetism, the charge of the electron, relativity, the speed of light, and quantum mechanics. Planck's constant. This is a quote by David J. Griffiths.
No, it didn't rhyme.
And sorry, it's not a poem, it's a quote. So the David J. Griffiths, American physicist and educator. All right, in any case.
Okay, well, we're charging into
uncharted
territory now.
We are indeed, because I gotta admit my lack of knowledge in terms of this, so it's gonna be mostly me questioning Dr. Leonard Kramer. But before we actually begin, you should probably see my face. So this is.
Oh, and by the way, what is this? What are we?
Wait, hold on
what
a
is
second.
this? Yeah.
What is this? What is this indeed? This is SG2 on Space, the only weekly space show. By the way, I do need to change this. We are, by the way, for everyone that out there, you may not have noticed any Facebook updates because my account unfortunately got hacked. So to watch this episode, I should say, just go to youtube.com/ and if you're watching it already, no doubt that's where you are already watching it, but just for future reference, future episodes as well. It's youtube.com/ at Shenge. So at SHENGE, and that has these videos past and present, and the live show is still Wednesday night 6:30 to 7 p.m. What has not changed? Well, support the show on patreon.com/ SG2 on Space, and definitely thank you to our supporters and patrons in the past and present: Kyle Baker, Sam Welsh, and Atum Ra, who last of which was helped produce the show for almost 2 years. Now, with all that said, let's bring in this guy. Who are you?
Hey, Shen.
Who are you? This is Dr. Leonard Kramer wearing his signature headband, as always.
My swag. Yep.
He's wearing his swag.
I'm sorry about your Facebook getting hacked. That's evil.
It is evil, and I was just thinking one way we can quickly catch the culprit is if they suddenly start pretending to do the space show, which they're probably not going to.
Yeah, probably not. So.
I mean, I definitely do need to get back the admin privileges for all these pages, even if I can't recover my personal page, because it's just ridiculous.
So you're negotiating with Facebook, with the Facebook.
I am initiating conversation, which I don't know if it's throwing into a black hole or whether there's actually somebody listening. So that is unfortunately the fact about this social media platform, where they have no, there's no number you can call. That's the problem. So
Mm-hmm.
I could spend the whole episode talking about my complaints,
right? But I was gonna say, so what did you want to talk about tonight?
The fine structure constant.
Oh, the fine structure,
the alpha
constant.
whatever.
Alpha.
Mm-hmm. Yeah. What? Okay, so if we look at it, what exactly is it? First of all,
well, a lot of physicists get real excited about it, and I came across it. I think. I probably saw it as an undergraduate, but I didn't understand the significance of it. But in graduate school, I took a class in advanced quantum mechanics, and we came to this what they call Sommerfeld theory about the line spectra of atomic emission spectra from atoms, for example, hydrogen, and I guess a lot of our audience knows that the emission lines are like lines of light that are emitted, like from hydrogen. If it's excited, then it's only accepting certain frequencies, certain wavelengths of light, and will emit at the same frequency. So it'll absorb and emit. And so there was a theory. This was a big mystery at the end of the 19th century, and it was originally resolved empirically, I don't remember who it was that came up with a formula that described it with a single integer n, which represents the energy of the excited states. But what was also observed very carefully at the end of the 19th century was that the emission lines that I'm talking about also had a split to them. It was like if you looked at it, from a distance, you would see a single line, but then when you looked very, very closely at it, they were split. And in around 1900 or maybe a little later, Sommerfeld, I think his name was Arnold Sommerfeld.
Yep.
He came up with he combined special relativity, Einstein's special relativity, with quantum mechanics, and came up with and was able to um, use that theory to explain these splitting of the emission lines, and those it's called the fine structure, and it occurs in, if you know chemistry, you know about the orbitals for the electrons and
Mhm.
that kind of stuff. So um, certain orbitals where there's some angular momentum, then there's quantum numbers that consist of n, which goes from 1, 2, 3 all the way up, and then there's other quantum numbers L, that J and L, that correspond to the modes of the angular momentum. And when those are involved in an emission spectra, then it's split. And his theory showed that. So there's no way to. So the interesting thing about it probably sounds pretty arcane, but the interesting thing is this constant, and what it is it's a constant, and it's almost exactly equal to 1 divided by um um I'm sorry, 173.
Yeah, this number, right?
It's
Yeah.
almost exactly 173. And so and it has no units. So what it means is we don't have any theory. There's no theory at all that allows us to derive this. In other
How how did he come up with did he just throw
Well,
random
I mean,
physics
I mean,
constants?
he was playing around with the equations that have to do with the emission from
Uh-huh.
the electron, if it's rotating in one direction versus if it's rotating in the other direction, and then also using special relativity, and and um, I actually have my textbook right here
Let
from
me see it.
from grad. Oh,
Here,
it's
what
it's
let
a
me see it.
it's a
One moment.
well-worn. You can see it's got all this. Yeah,
Physics
there
of
we go.
atoms and molecules.
Yeah,
With
and
this
it's falling apart.
it
Uh,
does look like it's falling apart,
it's
but
a
that's
well-worn, and
it's well
so
worn.
yeah, so I just went over that again, and I have a I'm a little bit of a savant as far as remembering
Let me see if
stuff
this
that I
is
learned.
accurate. Yeah, go ahead.
So some of my colleagues, classmates that I'm still in contact with are sometimes dumbfounded that I can remember
Nope.
stuff from, like, I can remember homework problems that I did, and all that stuff. So I do remember this, and I glanced over it again. So that's where it comes from. So that's probably not that interesting to our audience, but the neat thing about it is that this number
Hmm.
is a completely empirical number. It doesn't have any units, and it kind of represents the strength of the electric field um, compared to the quantum energy needed to ionize or to pull two electric charges apart. And so it's kind of like a normalized um, electric field.
I mean, we
Uh,
can look at the
Actually,
equation.
yeah, if you look at this, okay, so
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 E,
E
yeah,
is the elementary charge, and that's the charge on an electron. It's also the charge on a proton,
uh-huh.
right? And so we don't think that there's any that the elementary charge can be divided any smaller than that number. But you notice it has it's wed it's connected to a particular kind of unit called a coulomb, right? And so that's not that's the elementary charge. And then there's Planck's constant, which was, that was promulgated by Planck for the originally for the black body background, and he had little oscillators to resolve what we called about. I think we talked about the ultraviolet
We did
catastrophe one time.
ultraviolet
And so
catastrophe.
that's where Planck's constant comes from, and it has units also.
Joules
And
per Hertz.
joules per
Hertz
joules per hertz. That could be one way to express the units. All right, and then there's reduced Planck constant, which isn't very interesting. It's just Planck's
divided by
constant
2
divided
pi
by 2 pi. Then there's the speed of light, and it also has units. And then there's
meters
this
per
thing
second.
called electric constant, which is really, I know it by permittivity of free space, and that's sort of a scaling factor that gives you the force. If you have the distance between two electric charges, that sort of provides a scaling to give you the force between the two, or electric
Or,
potential. But
or
anyway,
yeah.
if you throw them all together in this form,
Mm-hmm.
and it doesn't have any dimensions. So alpha doesn't have any dimensions, and it's almost exactly equal to 1 over 137. So 137 is sort of it's not exactly 137. It's a little bit more than that, but it's sort of wild that you can throw all these things together, and it is what it is. It doesn't. And so people have studied this, and they said, look, if it's just 5% bigger, then stars won't form, because the way the universe, or the universe will if this number were slightly different from what it is, then the effect on the entire universe would be that it kind of wouldn't exist, or it would only be short-lived, or carbon wouldn't form. We know that the stellar explosions create the heavier elements. None of those elements would form, and so it's said to be a very critical, finely tuned number that determines the state of our universe. And so I just wanted to point that out. Yeah,
So
it's related to the probability that an electron will emit a photon. And so all of these things are all kind of tied together in Sommerfeld's constant. I read that. Okay, we're reading about Eddington here. Eddington was famous for doing the experiment with the viewing the eclipse to
mhm,
verify general relativity, to this, the aberration of star
right.
positions from gravitational curvature in an eclipse. But he also he went a little bit out there, talking about, he thought there was something mystical about
About the number
137.
137.
And yeah, and he tried to argue, it's a prime number, and so that's kind of like interesting, or kind of a clue. And so he thought that there was something in it that was mystical or magical, that made it what it was. But then by about 1940 or so, the experimentally derived values showed that it did deviate from it by about, I don't know, 0.3%, 0.2%, something like that. So that's probably not the case. But if we were to send messages to extraterrestrials,
Is that
w-
what we will send?
yeah, we should send that number. Just send 137, okay? And they'll know what that is, right? And the other thing we could send would be maybe the ratio of the proton to the electron mass, which I think is around 1,830, but you can check me on that. And those kind of numbers are universal throughout the universe. And
What is I mean, I understand how um I mean, you can put these very physics constants together and derive this, uh, I suppose. But
well, I think Sommerfeld, he rigorously applied the special relativity to the electron motion. So there was rigor in his equation, but he had one constant that he had to measure the distance between those split energy levels, and then backed out the constant, and it came out to be this number. And then we end up seeing it everywhere. So we don't know how. It could have been that in the early late 80s, early 90s, when string theory came about. I imagine that people were like looking at string theory and trying to think, well, it's a theory of everything. You know, it um, the fine structure constant should fall
Should
out of
should,
it,
should fall
but
out
it
of
but
it.
it didn't.
It
I
didn't.
really think that string theory is a. We can talk about that sometime too.
Yeah, I mean,
I
I think you
I
voiced your
I think
before.
it's sort of a disappointment. I think it hasn't really developed into what there has been new discoveries, like we're pretty firmly certain, we're pretty certain that there's something called dark matter, which we've talked about before. And string theory didn't pop out of dark matter. A theory of everything would
Is
produce that. So
going
I
back to fine structure constant, how do
yeah.
you empirically get it?
Well, um in my textbook here, I have like the formula and
Hmm.
everything related to the fine structure constant. So it will tell you how far apart these multiplet. It's called multiplet fine structure. You might be able to show a diagram, find a diagram of that, but the distance, the distance in terms of normalized energy between those two
Hmm.
is proportional to I think the fine structure constant squared, or something like that. And so you're able to back it out empirically by just looking at the photograph of the emission lines and seeing how far apart they
It's
are
for
relative
a hydrogen atom
for a
or what?
hydrogen atom. Yeah, you can. And and so there'll be.
Like, let's see here. Let's see. If we look at this, what do we see?
Well, those are orbitals. I mean, those are the orbitals for hydrogen. So you'd want to look up something like multiplet structure or fine structure of hydrogen atom. And I was just looking at it here. See?
Whoa,
Oh,
not
so
quite. This is an interesting way of portraying. Okay,
yeah.
so
So this is for helium, but you see, those are the energy levels, and
uh-huh.
I think over on the left is the non-relativistic, and then when you add the relativistic theory, then the lines split apart like that. So those are the energy levels of and that's for helium.
The,
So
okay.
I mean,
Is this let's see.
here's see, there's a bunch of them. So
I
that
definitely
theory,
I do see it. Yeah.
yeah, it's.
When the the drawing on Wikipedia with that squiggly thing, what is that exactly?
Oh,
Let me
that's a Feynman.
wait,
I think
not
that's a Feynman diagram.
no,
So,
where is it? This. Oh wait, if I can show it actually. This thing.
oh,
Eighth order.
so this is a Feynman diagram, and I don't know what that particular reaction is, but um, so this is a way of diagramming or putting together all of the different kinds of reactions that subatomic particles with collisions and emission, exchange of particles, and so forth, um, will occur, and then you can account for the probabilities of each one of those to determine things like decay rate and so forth. But that's not what I was.
I
That's
don't
not.
know why it's on that page then. Yeah. Okay.
Yeah.
But the fine structure constant in terms of you're saying like if we look at a hydrogen atom, it has to do with the energy
It has to do with
atom,
the energies of the emission lines. So
energy of the emission.
hydrogen will emit at different. Yeah,
There we go.
yeah, there it is. So,
Okay, let's take a look at that.
so Sommerfeld was able to use the a rigorous, and you notice the S shell doesn't have any, but it's a P shell. The P shell has some angular momentum
Hmm.
associated with it, and that's the thing that's causing the splitting. And the exact number, the exact value of the splitting is determined by the Sommerfeld constant. And it turns out that it has profound effects in the entire universe. In other words, if it wasn't exactly what it was, I don't know, within a few percent, we wouldn't exist. So,
What would happen to us? Oh, we
well,
just wouldn't exist.
the universe wouldn't exist. It would be it might we might there might be a big bang, and then it would only last hundred
Ah,
thousand years.
this is
You
it.
know?
This where it says fine structure, right? Right here.
Yeah.
Between the 2p 1/2 and
Uh huh.
2p 3/2.
Yeah.
That that difference right there, I suppose.
Right.
Um,
So it's
it-
interesting. I think it's interesting.
can you explain? Is this so? Earlier, we were looking at those equations. Um, how does it relate to these two energy levels? How does a dimensionless constant come from that?
Well, I guess I did explain that, but let me explain it in a different way. So
Hmm.
Summerfield studied this problem of the splitting. In other words, the
Hmm.
splitting of those lines. You see how it's been magnified, and then you see two lines. That was observed, right? And so the physicists, and it was seen everywhere, and so the
Hmm.
physicists were trying to figure out, well, what's going on here. um, what is the physics, what's going on inside the atom that's making that happen. And
Hmm.
so he had this idea that I will apply Einstein's special relativity to the electron motion in the atom. And in those days they just used what they call Bohr model, which is that classical kind of schematic of an atom with that's has electrons that are orbiting around like planets in the solar
Right.
system. And so he applied that equation, or he applied that theory, and determined that there were two solutions to the emission spectra, uh, which was solely dependent upon the uh, the special relativity. The idea that the mass changes depending on which direction it's going, how fast it's going, and so forth. And then so the theory the that theory made the line split, but there was an extra empirical term that that didn't come out of the theory. It was an empirical term that he needed to scale that. So that was alpha. So he just stuck alpha in there, and then he measured the distance and came up with and produced that theory. So it's not complete. We still don't know. And 100 years later, 110 years later, um, that theory is still not complete because we don't know what alpha is. We don't know where it came from. Is that Am I
I,
making sense?
I think
No.
so. I mean, if like looking at this, the
So
delta E expressed as this, right?
yeah, it's the
Then he just.
ratio. Yeah, it's sort of the ratio of the potential energy between two charged particles in general,
Hmm.
and the energy of a photon with the wavelength of that distance, right? And so it turns out that the photon has 137 times more energy than the potential between the two particles. But that's not a principle. That's just a uh,
Yeah,
sort of,
I get
yeah.
it. Like this kind of
Uh-huh.
relationship, it's you could derive it, but it's not like anybody could explain why it's all related like this.
That's right. That's right. Why
Okay.
is that? And of course, in physics and also in engineering, these kind of dimensionless parameters. Well, I mean, it's obvious that nature is imposing some kind of relationship on those four constants. See, the E is a constant, epsilon naught is a constant, H bar isn't constant, and so is C. And so nature tells us that those are connected in that way, right? Because that number appears in the physical processes, but
Right.
we don't have any idea. I literally don't think anyone has even any idea about where this comes from. String theory didn't give it to us. Field theory, the standard model, it's a parameter in the standard model. Remember we talked about that one time? So this
Yeah,
is
we
one
did.
of, yeah, this is a parameter that has to be supplied for the standard model to work. And
Right. And it's
so
like, here you go. And the standard model does not explain where it comes from. It just uses it.
no, it just uses it. So if you want to win a Nobel Prize, you just need to come up with a theory, some extra, maybe there's some kind of variation on string theory or another dimension that you can add to space-time or something like that. Because we have non-dimensional, dimensionless parameters like pi. And so
Mhm.
it's kind of obvious what pi is. Pi is the ratio of the circumference of a circle to its diameter, right? So that's easy. I mean, that's easy. You can just take a circle and measure it, and you see, you kind of like see the geometry in that. But this one is of that nature, but it doesn't. We don't see what the connection is. So it would be almost like with pi, with the number pi. You take the circumference and divide it by the diameter. I think it's the diameter, right? Yeah. Um,
Right.
and so and so I would have I would have a formula that's analogous to this, where I would have the circumference in the numerator and the diameter in the in the um, denominator, in the numerator denominator, right? And so you can see that just comes out to be pi. And I don't really need to, I mean, I can still talk about a fundamental mystery about why is it pi? Why is it that number, right? But I feel like I have a better handle on it because of the,
To change this number, I mean, you would have to change either, I guess, E or H or C, right?
well, you could change any of those things and it would
But then that's
change.
not
Yeah.
that obviously it's huh.
Yeah. So the
Interesting.
term that we're looking at right now, it has a K in it. So K is absorbing the epsilon naught, the permittivity. It's like a wave. It's like a wave
Oh yeah, yeah,
vector.
yeah. That's
Okay.
right. That's just
So,
another way of
and I
writing it.
also want to emphasize that it's not exactly 137. It's showing it as 137 here, but it's something like 137.05, I think, or 3. And then on and on, dot dot dot.
Right, right. It's
Okay.
just like what we said earlier about edit and thinking was
Uh-huh.
exactly 137 and it wasn't.
Yeah. So, um,
Interesting.
interesting. I think that there are a couple more dimensionless parameters that go into the standard model, but none of them are as important as this one.
The meaning of the fine structure constant. I don't know. I just randomly found this archive.org article.
Oh,
Have not read it, but it might be interesting.
yeah. So
Oh,
it's just an abstract. Oh
no,
no, no, it's a paper.
no, it's a paper. It's a
Okay.
paper that is only 9 pages long, but and I
Oh.
don't know where it leads, but might be an
Well,
interesting read.
like I said, well, the meaning, I don't know about meaning or anything like that. It's just that it is what it is.
Is this something which is under active research, or did people just give up and accept it is what
Oh,
it is?
I, I don't, I don't think that there. I mean, like I said, string theory would, you know, if string theory could come up with this, then we'd hear about it. But I think that I mean, it could be that string theory kind of has like, string theory is the space shuttle of the particle physics. It sucked up all the resources, and so people
That's.
that was mean.
I
I mean,
mean,
I didn't really, yeah.
I no. I mean, you're welcome to your views, of course.
Yeah.
I mean, well, you may argue like what has it contributed so far that we didn't already know,
So
or can prove.
right.
Hey, so This was an interesting article I just found where they apparently, I mean, it's not explaining where it comes from, but they're able to
Uh-huh.
apparently measure it directly.
Well, I mean, people. I think it is kind of incumbent or important to measure it astronomically, measure it. Use maybe there's some measurement that can be done with the hub with the Webb with the James Webb telescope to measure this fine structure constant in 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 very ancient, because we're looking way back in time. We're looking back, tens billions of years in
Right.
time, and so it would be nice to be able to observe the fine structure. It actually shouldn't be difficult because you can just look at emission spectra, and if you can resolve it carefully enough or finely enough, then you can just measure it the same way that Sommerfeld did.
The just a note, apparently fine structure constant is a constant that appears in other places as well. Like this experiment, apparently, they sent this light beam through a spectral material, so it changed the direction of polarization, and this angle is directly related to the fine structure constant.
I think that's not surprising. So
Hmm.
so they were able to engineer do some kind of engineering that would allow them to very precisely measure it to more add more digits to it. I don't know that we're gonna discover anything fundamental just by measuring it.
I
Uh,
don't I don't think so. I mean, I think it's more of a
yeah,
hey, we could get it to be even more precise or
yeah,
accurate.
but
Yeah.
being able to measure it in the past from astronomical observations, that's something valuable. It might also be valuable to show that it's isotropic. In other words, different places that you look, different directions you look in astronomical observations. Does it give you the same number? So it probably does.
Hmm.
It's probably something fundamental in the in the structure of the universe, just like some of the other parameters. But ultimately, ultimately, that's the story. Y- uh, let's see.
Has this constant changed in the past?
I do not know of any papers or anything that describe that it is anything other than a constant, both in location,
Right.
and also in
So
time. So,
the result from a
but
2020 study, the fine structure constant has not changed in time. The researchers combined the results with all the previous, resulting in 320 measurements spanning from a billion years in the past to around 12 billion years in the past. A good chunk of life. It shows that the fine structure constant is constant.
yeah, so some people have talked about the multiverse, which I think we've talked about before, and that the idea is that there's many universes, or that
Hmm.
every time a universe is created, then these numbers get set somehow. But I don't think there's any science to that. I I
Oh,
think that
it's just
that's a
saying like every possible universe is out there. So
yeah,
there's some universes where this constant is like 1/56.2.
uh-huh.
Say I just
And
threw a number out there.
and then the other thing that people say is, well, and the reason you need that is because the reason you need a multiverse
Hmm.
is that, and I don't necessarily buy into this. It's just that what people say about the multiverse is that explains why it's finely tuned, because we got we got the universe that is capable of supporting
You,
life,
you're talking about
right?
the
Yeah.
anthropic
Yeah, so
principle.
there's like, let's say there's an infinite number of universes, or billions and billions of universes, and some of them only last a little while. Some of them, there's no atoms, formed other than hydrogen. There's no carbon in some of them, and it's just the
Right.
whole Marvel universe, and Doctor Strange and all that stuff is
I
going
mean,
on. You
according
know,
to
it
this, I mean, those
right.
universes might exist
Okay.
as well.
So that explains why it's so finely tuned, because
Right.
we got we 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 exist in the one that is capable of supporting our life. Now, I actually don't think the universe is actually that um that likely to produce. We've talked about that
Did
before.
you, did you
Yeah,
did you say you don't believe in the multiverse?
I I don't find it
Yeah,
very useful.
multiverse in this context. That's what I mean.
I don't find it a very useful um, proposition.
Okay.
Okay, you know, if you can produce something observable it's basically um, propounded for for the reason that we don't like the idea that our universe is special. We have a we have a animus
Right.
against it.
And also the fact that we have yet to develop theories to explain why certain fundamental physical constants are what they are. So,
Yeah, of course it doesn't help because then you have to explain why it comes out of a you know a throwing dice. Okay, you
yes,
still have
that
that
is what
problem.
you're saying, right? If you
So
believe in this, you're
yeah,
basically saying it could have
so
been anything.
yeah, so and yeah, oh, I see you talking about Nick Bostrom there. Okay, so he's one of these people who isn't he? Doesn't he get into the simulation hypothesis
Well,
and that sort of thing?
he's a philosopher, so
Uh-huh.
yes, I think he does go into that. Um,
So simulation is a religious notion.
which it's
It's a,
funny you say
it's
that
not
because they philosophers could use many logical arguments, but sometimes you're saying it can border on faith, right? I mean, when you think about it,
the
like what?
first time I heard about simulation hypothesis, and what is simulation hypothesis? It's this idea that there's some super advanced intelligence that's
Mhm,
running a computer program
right.
essentially, and that in the computer program there are these avatars of beings, intelligent beings, of which one is Shen and one is Leonard, and all the other avatars are all living their lives, and so everything is a simulation. Okay, so presumably the super advanced being
Hmm.
is doing this for a purpose, and and I just wanted to mention the first time I heard about this, I thought, well, I heard about this before in Sunday school. You know, it's a there's a there's in the Bible there's a book called Genesis, and it talks about a super advanced being who creates a universe and populates it with
I mean,
and it comes out of the Bronze Age, right? And
that's so
and
funny.
so not only that, it's like sometimes the super advanced being, likes to play, likes to
Right.
change things, like he'll part the Red Sea, or he'll have some guy who will walk on water. You know, so that's the first thing that occurred to me. And when I tried to explain it to people, they did, oh no, this is serious, this is a serious scientific idea, and I don't think so.
You argue with that because how do you even
I
prove it? I
Yeah,
mean,
I
it's,
don't.
it's basically like religion. Yeah.
It strikes me as a genesis, as an archetype, some kind of archetypal
So
belief, that like a Jungian archetype, in like it's inside of us to think that, to believe that, and so we try to produce it in a way that's palatable for um, a modern culture, but it's the same theory, and the fact that they can't hear it, they can't see it themselves. When you pointed out, look, this simulation hypothesis is something that was proposed in the Bronze Age, right? They just think you're crazy. They don't buy that, but it's so obvious to me. So anyway, but that's me. I'm not actually not from this planet.
where you
I
where
I
you
oh,
you're
I'm from
admitting
I what?
you're finally admitting you're not from this planet.
Yeah, I'm not. I'm really not from this planet. I do
I mean, that could explain a lot of
I
things.
do communicate with the mothership, and they they sent me down here to observe, right? Observe the hominid.
What have you noticed so far of our
Oh,
world?
they hominids do funny things. We could get into that. I have another
Okay,
time. I'm
that's fine.
of course I'm joking. I
Well, I mean,
I
I
don't.
think you're joking. So,
Yeah.
I still. All right. So normally at this stage, what would you like me to say?
Oh, you would talk about the mothership, probably.
I mean, sure. Let's talk about the
It's
mothership
been a
by.
pretty good conversation, I have to say.
I
I
have to
won't.
say, why
Yeah.
not here? So I'm
What
just
do you got?
gonna. There is a video, but the video is really corny. So why don't we just? I don't even know if this photo is real. I mean, what does that look like?
I don't know that any of them are real. So
Like, what is that? So this is the. What is that?
somebody's practicing with their blender.
That's a real picture. I mean, I don't know.
Yeah.
What's your? I need to see where this photo comes from. So I'm just gonna read through this thing, which by the way is from this website called where I get a lot of these, which I'm not saying it's, which I find it entertaining. UFOcasebook.com. So former manager, defense contractor, used to run Area 51, claims remains were once recovered that include both the flying saucer and living being. Blah blah blah. EG&G ran the notorious site, and a senior manager there. I whatever the name is put out there. I don't know if this person's
Uh-huh.
real. Alfred O'Donnell has since claimed they did have a flying saucer that had been recovered from New Mexico. Interviews investigative journalist
Yeah.
George Knapp also claimed a live being was recovered. We didn't know who it
Uh-huh.
was. To tell you the truth, we couldn't communicate with it, and we didn't know where it was from, and we didn't know what to do with it. But rather than the image of an alien, we all think of a large, what? I don't know what that is.
What? You don't know what is?
Large, hideous being was found. The Liberation Times reported the story in February and added the former female employee of the defense contractor at Holmes that never also had a similar
Yeah.
experience. Blah, blah, blah. So she claimed that she knew about crash saucers, recovered materials, and what sounded like a Roswell type incident. The woman allegedly refuses to have meetings with Knapp over supposed intimidation by unknown agents in the past.
Wow.
Okay. And then there's this goofy video, which I'm not going to play, but I wonder if
So
this picture has anything to do with it, or just randomly put there.
I believe that's a work of art. I think that maybe it was using the Blender software or Maya or some 3D stuff.
I think that's
Yeah.
not a real picture, right?
I think
I
that's
think
not
that's
a
the
real picture. Yeah. Photoshop, something like that. I will say EG&G is a real company, and
okay.
they do secret stuff, and they do stuff for the Department of Energy.
E.g., Egerton, Garmachon, and Greer, I guess.
Yeah.
And then the other one was what was it? Holmes and Narvard.
That one I don't know about.
I think
But
that one's also real.
yeah.
It is real.
Yeah.
So I mean, I don't know. I think if you're gonna
there
put
aren't
up
any. There aren't any aliens. So.
All right, Leonard has definitively said it. There
Yep.
are no other aliens,
Other,
except for him.
except for me.
Because
and those
there gotta be at least one to communicate with the mothership.
And my friends on the mothership. That's right.
I mean, what are they doing here?
What are they doing here?
Yeah, why are you here except to report to the mothership?
That's right. An object of study, planet Earth. All right. I think we should
call it a day.
But it was fun and it was a good conversation, and I think we'll do this again.
You can imagine yourself going into space, I guess, sort of. I don't know why nothing's showing up here.
Yeah.
Try to make it full screen and then just messes up everything.
Oh.
But that's the wonders of, or not wonders of technology, I guess. All right, so everybody, considering that I can't seem to get the space ambient video up, you're just gonna have to suffice with Leonard's headband.
Okay.
In my face. So, as everyone knows, this has been SG2 on Space, the only weekly space show. YouTube.com/@Shenga. And you can, of course, support the show, patreon.com/SG2 on Space. We will be back next week.
We will.
As always, next Wednesday. And hopefully can also get the Facebook thing reattached and
what is it? Like, subscribe, share with your friends.
Right. For right now, go on that, you can check out youtube.com/shenge for a few of the past episodes. And yeah, and like, subscribe, and all that jazz, and share. So, all right, we will see you next week, where no doubt we will talk about another exciting topic of interest in science and space. Look up, because you never know what you will see.
Good night.
Namaste.
Namaste.